All right. Today we're going to take a look at the specific heat practice. There's a little bit of review kind of built into this, but I'd like to be able to show you how I would set things up where you can choose which of these formulas to use, and you understand how you should use them, organize it. And at first glance, they look kind of intimidating, but if we keep organized, I think you'll see that it's not really like crazy mathematics. It's just organization and matching. So, a little bit of review. Specific heat. I hope you're at a spot now between lecture and class discussions and examples that you get specific heat is just the specific amount of energy it takes to raise a kilogram of a substance a degree Celsius. And I hope that you understand that heat is really just an energy transfer. And we know that heat will transfer from high to low, or the cutesy way of saying that is heat flows high to low. And when we take a look at specific heat, the confusing part is for some kids, if we say something has a very high specific heat, they just assume, okay, well, if the specific heat's high, then that must get high temps. And it doesn't actually work out like that. Again, specific heat is how much energy does it take to raise a chunk of something or a kilogram of something a degree Celsius. So if we look at these common examples that we've been using, if you look at water, water has a high specific heat. That is to say that it takes a lot of energy to raise a kilogram of water a degree Celsius in comparison to other substances. So think of it like this. Imagine I go to my tap and I fill up a pot of water and I carefully splash in 1 kilogram of water and I put it on the stove burner. And then I've got a little metal bar and it's a kilogram of aluminum. And I turn on both burners at the exact same amount of energy. I know that if I'm holding on to that metal bar and I place it into the burner or the flame of that stove, and I've got my finger in the little pot of water on the other side, that my hand that's holding that metal bar, it's going to get burnt first because I know that that metal's going to heat up faster. Or if you take a peek at some of these other examples here, if we use like wood and steel, or you know what? You're all fancy lads and fancy princesses, and you don't use steel. You're just using silver. And I've got my little stick to roast some weenies, some hot dogs at the old campfire, and you've got your silver rod. And we both put hot dogs onto me with my old wooden stick, and you with your silver rod. I think most of you kind of see that if you place both those into a campfire, that wooden stick isn't going to heat up or burn your hand as quickly as what that silver rod was. Why? Well, because silver has a lot lower specific heat than what the wood would. So other things that we got to know before we get through all this that I hope is kind of review is what each of these stands for. We've got Q, we've got M, we've got C, and some kids will call this triangle T, but I hope you're saying delta T, or you know that this is the change in temperature. And Q, it's going to be our abbreviation for energy. I get it. There's no Q in energy. Why would they do such a thing? I mean, there's other languages than English. It just is what it is. M is always mass. When I was a youngster, the way I remembered that C was the specific heat was that had 2 C's in it, and that is the specific heat. And again, this isn't delta T. This is our change in temp. So we got to keep that straight. If you're using this formula sheet and the example sheet that I gave you come quiz or test time, if you want to jot this down on there, I think that's fair game. So these abbreviations all have their own units, or what we'd measure them in. Joules, just capital J, that's the unit that we're going to be using for energy throughout this specific heat unit. Mass, primarily kilograms. Sometimes we'll be using grams depending on the given example. Specific heat, this is kind of the one where it's all squished together, or it's the really complex looking unit. It's going to be joules per kilograms degrees Celsius. If you look down here, there's always that as a reminder as well. But sometimes kids just are like, well, how could this have all three? You got to stop and think, specific heat is how much energy does it take to raise a kilogram of something a degree Celsius? So this is what specific heat is. So it takes all three of those. And for temperature, I think all the examples I give you throughout this unit, they're going to be in Celsius. Remember, we're done with gas laws for now. There's no conversion to Kelvin. Don't add 273. Just if it's Celsius, it is what it is. Just leave that be. So understanding these and then being able to read through a problem, and if you've got a unit, you know what to organize or plug it in as, or if it's asking for a specific example, you should be able to kind of work your way through all this. So this is fair game come quiz or test. Feel free to bring it. I'm sure there's extra copies in my room, but let's take a look at an example here. So we'll do number 1 because it's the first one. And I haven't even read this yet, but I know that this is all specific heat stuff. And I know that I'm going to have to account for all this stuff. So with that being said, let me try to get this a little bit better in frame there. Okay. I know that I'm going to need to be able to read through this and pull out Q, M, C, triangle, T. And now I can get started. So this says I got a 0.5 kilogram sample of aluminum, and it's provided with 15,000 joules of heat energy. What will be the change in temperature of this sample of aluminum? All right. I don't want to work with all that. I want to try to organize it through here. So it looks like I start off with a 0.5 kilogram. It's a number, right? Probably I'll need that. I see it's kilogram. So I know that if we're talking about grams or kilograms, that's got to be an example of mass. So I'm going to take mass 0.5 kg. Sample of aluminum. All right, the fact that this is aluminum, I think that may come back to be useful, so I want to keep that straight. It looks like there was 15,000 joules of heat energy. So if this just said joules, 15,000 joules, I mean, I could refer back to this to figure that out, but it comes right out, tells us 15,000 joules of heat energy. Oh yeah, there is no energy. Q's your energy. So I'm going to put the 15,000 joules up there. Keep reading. What will be the change in temperature? All right, well, it sounds like I'm looking for the change in temperature of this sample of aluminum. So I got to have all these accounted for except for whatever the one variable is I'm trying to solve for. It looks like I'm trying to solve for the change in temperature. I don't have the specific heat here. Nothing told me what the specific heat was. So I know that this sample is aluminum though. And a lot of times throughout the problems in this unit, I'm going to just pull from this little example list. This isn't the end all be all list. Everything's got its own specific heat, but these are some common ones and I just put it on your formula sheet. So regardless of all that, aluminum 900. So the specific heat of aluminum is 900 joules per kilogram degrees Celsius. And again, the reason that is, it's how much energy does it take to raise a kilogram of something a degree Celsius. So this is pretty good, right? I mean, I can actually take this sheet, set it aside, and this is really all the information that I needed. I'm looking at this and I've got the energy, I've got the mass, I've got the specific heat. I'm trying to solve for the change in temperature. So a problem I find that some kids get into is they just randomly pick one of these and they just randomly start to plug stuff in. And that's not really a good way of going about doing things. You're guessing, and you don't want to guess on this. You want to be certain. So if I'm looking for the change in temperature, this is the only formula that works for me. I have to use that one. So remember, we're looking for the change in temp, and the only formula that's going to work with that is, if you're looking for the change in temp, it's equal to Q over MC. So from here, I can do some matching, right? I have to match things in the right spot though. Q goes on top. So that means that my value for Q has to go on top. So there's 15,000. M is here, all right? So my mass was 0.5 kilograms times the specific heat, which this particular sample was aluminum, and we said that, all right, that's got a 900 joules per kilogram degrees Celsius of specific heat. So now I'm like donezo with that, and I got to do a little bit of math. So I'm going to reach for my calculator, and I'm going to take care of this bottom part here first. So if I go 0.5 times 900, I got 450. Slide over my 15,000. I'm going to clear that out. 15,000 divided by 450. And I got this. So with my rounding, you know, I always tell you just go to the 100th. I'm looking at this 3. That doesn't appear to make that go up. So I would just call this 33.33. 33.33. Okay, what? Well, we said it was the change in temperature. What are we measuring temperature in? Well, in this particular unit, we're using degrees Celsius. All done. So what this tells me is if 15,000 joules of energy was applied to a 0.5 kilogram sample of aluminum, I would expect there to be a 33.33 degrees Celsius change in temperature. And it's just that simple. So looking at these guys here, again, can be kind of intimidating. But as long as you know, look, we're in the specific heat unit, each of these problems I'm solving for, I got to basically look for what the variable is that's unknown and then figure out the 3 that are, match them into the only formula that you can actually use, and you should be in pretty good shape. So one other thing I want to go through with you real quickly on here is question 3. I asked you what type of substance heats up more quickly if an equal amount of heat energy were applied to them. This is just kind of a bit of review on conductors and insulators. So if we are going to add an equal amount of heat or energy to a conductor and to an insulator, I would expect the conductor to heat up faster. And the reason, by and large, that they heat up faster has to do with those loose electrons on their outskirts, and they get excited quickly. Therefore, they move faster, which is really to say a hotter temperature. So the substances that do not heat up quickly, they're going to be called insulators. And the reason that they don't heat up so well is really the exact opposite. They've got relatively tightly bound electrons. There's not going to be as much movement on the outskirts there. And if there's less movement, you should know by now that movement's really temperature. So we did the first one there. If you've got questions, concerns, please feel free to ask me in class or shoot me an email. One other thing, just before I forget, if you notice that you've got a temperature range, like look way the heck down here, like on number 15, where the change in temperature was like -5 degrees Celsius to 25 degrees Celsius. In this particular problem here for number 15, you're trying to figure out how much heat energy. So you'd have to figure out here for the change in temp, right? What you would be plugging into your formula for the change in temp. In this particular guy, if it went from -5 to 25, you had a 30-degree change. So some of them might just come right out and say, look, it was raised by 7 degrees or it cooled by 4 degrees. Some of them are a little bit trickier, but if you get that range, that's what you got to do there to plug it in for the formula on change of temp. If I lost you with that, like I said, please feel free to see me in class or shoot me an email. Take care.